So this version of delta G, in addition to using the Gibbs equation, we can use, although we don't call it Hess's law because technically he just worked with enthalpies, it's the same functional thing where we add, multiply reactions, and we can multiply them by coefficients, and we add them together to get new reactions. So if we look at this balanced equation here, we can see that these two equations need to add up to our bottom equation. And to do that, we've got to reverse a reaction and cancel some things out in order to get to our target reaction. So the first thing we see is that we've got sulfur in our target, and we've got sulfur here, 1 mole as a reactant. So that first equation is actually really good. So let's rewrite that first equation. So sulfur plus 3/2 oxygen makes SO3, and delta G is negative 371 kilojoules. So that's good. Secondly, the easiest thing to look at, we've got 1 mole of SO2 as a product, and SO2 is a reactant over here with 2 moles. That means we need to take this second equation and do negative 1/2 of that second equation. So reverse the reaction and divide by 2. That gives me SO3 turning into SO2 plus 1/2 oxygen. And if we change that sign for delta G of the second equation and reverse it, now we have a positive 71. Okay, and we add these together. The sulfates, the SO3s cancel out. I'm going to have half an oxygen cancel out. That leaves me with 1 oxygen. And we are left with our target equation. Sulfur and oxygen make SO2. We can add our delta G's together. Negative 371 and 71 gives me negative 300 kilojoules. So we can use, well, air quotes, Hess's law to figure this one out. And then if we can do this with delta G if we can do this with delta H and delta S, we can do this with delta G as well. We just need to show our work carefully with our summation equations. So delta G equals, big bracket, 3 moles of carbon dioxide, products minus reactants, and the summation of them plus 4 H2Os. Everybody usually does this part okay. It's this negative sign that gets distributed in the reactants. 1 C3H8 plus the sum of 5 O2s. Here it's important to remember this does not work with delta S, but any element in its natural state will be 0. So we have some predictive properties there. Since we have oxygen, gas, diatomic, those will be 0 for delta G and delta H, but not delta S. S's are actually entropies. They're real things. None of the S values in the back of the book are 0. So watch out for those. Those are very common questions. If you look all these up and plug them in very carefully, you should get negative 2,074 kilojoules. This is perhaps my favorite slide in all of chemistry, because when you look up the delta G values in the back of the book, diamond and graphite, you have to switch the order to go products minus reactants. Delta G is the graphite minus the diamond. And what you get is 0, because graphite is the natural state, minus 3. And when you do that, you get delta G is negative 3, which means this reaction is favorable. Diamond turning into graphite is a favorable reaction. So, my advice here is always to not buy diamonds when you're proposing or getting proposed to later in life. If you really want to say love, and lasts forever, it's graphite, not diamond. Now, of course, this isn't truly the case, although thermodynamically it is diamonds are not the stable form of carbon, otherwise they'd be everywhere. They form deep underground under very different conditions. So why doesn't diamonds turn back into graphite? This is our big reminder that this has nothing to do with kinetics. Even though it's favorable, the kinetics is not favorable. So this is under kinetic control. So if we had a delta G plot, so even though this is a favorable state, this activation energy is so high that it will not happen. There's no path for it to get over to the favorable products state. So the kinetics prevent this from happening, even though it is thermodynamically favorable. And that's what we want to think about. If it should happen, but it doesn't, there must be a kinetic reason, because the thermodynamics is in its favor, it just doesn't happen. If you want to get rid of diamonds and turn them back into raw carbon, perhaps you need the heat of the fires of Mordor to break it down further. And maybe then you'll have enough energy, activation energy, to get it started. And since delta G's are related to equilibrium, we can calculate those with our delta G equation, our equilibrium delta G equation. We know if products are favorable, then K should be bigger than 1. So delta G, the equation is negative RT natural log of K. And we're just going to plug these in and go back and forth between them. Conceptually, it's more important to know the sign of delta G is related to the ratio of K, greater than or less than 1, positive and negative. We won't calculate these often, but nevertheless we can do it. The gas constant here for R is 8.314 because it's the joules version of that, so we need to watch out for that. Otherwise, this one's pretty straightforward. And since that's in joules, we want to watch out for our delta G's in kilojoules. If I plug all of this in, negative 454,000 joules equals negative 8.314 joules per mole Kelvin. That's the gas constant in joules. The temperature is 298. Cancels out the Kelvin. And then natural log of K. Okay. And if we rearrange that and we solve for our natural log, which is the second natural log button, e to the x, K is going to come out to be 3.82 times 10 to the positive 79th power, which is huge. And delta G is very favorable, negative 454 kilojoules. So that favors the products pretty heavily. We can see that with the equilibrium also. So this is a very favorable reaction. This is a redox reaction with the aluminum stealing electrons. The aluminum giving up electrons. And it's just way more stable in its ionic state, and the chromium will come out and be in its solid state and steal the electrons. So this tells us a lot about the stability, because the products are favored and the thermodynamics are negative, that it's driven very highly to the right. So we get some interesting conceptual questions then with delta G's. Just because we have a delta G value that's positive, the reaction will not happen on itself. But does that mean it can't happen? No, it can still happen. We just need to add energy. Few systems are ever fully closed. Here we've got photosynthesis, for example. Photosynthesis has a delta G value of 2,000 kilojoules. How in the world does that process happen? How do plants take carbon dioxide and combine it with water? Well, the sun gives them energy to do it. As long as you overcome this value, you can get this reaction to happen. So a positive delta G just tells you the energy that needs to be overcome in order for a reaction to happen. Because all reactions are reversible, this just gives us the energy requirement. Charging a battery works the same way. A battery in your phone will is favorable to run your phone. It'll drain the battery. It does not go back on its own. The reverse reaction has a positive delta G, but if you plug it into the wall, you're adding electricity, which is energy. You're adding energy to overcome that and reverse that reaction to get back to a favorable condition. These next couple of slides are goofy. Just kind of listen and you'll be fine. Cycles in biology that got smuggled into the AP Chem curriculum. There's this interesting, if we talk about ATP and ADP, we talk about the misconception about breaking bonds being an exothermic process because you have to put energy in to break them. That's actually backwards from biology. But what they're talking about actually in biology when they say ATP to ADP, they're not actually talking about delta H and exothermic. They're talking about delta G being favorable. And it's an entropy, must be entropy driven to do that. But there's a cycle. So how does the reverse reaction happen? We know that energy needs to be put in for the reverse reaction to happen. And any cycle in the body has to have something helping it to get back to its natural state. So what is that helper that helps it get back the reverse direction? So let's look at a couple more pictures. The vocab word that they use that we need to just recognize, and I think the only way this could ever come up in an AP chemistry exam would be a multiple choice question, and it would be so oddly like a sore thumb sticking out that you would see it. It's called coupling. One of the reactions is favorable, this one, and one of them is not. So how do we get back up the hill for an unfavorable reaction? And the only way that we can do that is with a separate reaction that helps overcome the activation energy of the reverse process. There's mechanisms involved. There's all sorts of things involved. We don't need to identify them, but we just need to know that we need helpers to couple with them to get them back to its unfavorable state in a higher end delta G, higher free energy. And this is just what the final process looks like. How do you get any cycle to happen if one of the reverse directions is not favorable? And the answer is you need to couple it with something that is favorable to help it get back to the reverse state. You need energy from an outside the system to come in.